This here is the lane detection script as we left it in class. As we can see from the windows, the process involves snipping, masking, and blurring before we could finally start identifying lines. The final window shows us the lines identified by the cv2.huelines function. As is right now, we're still some steps away from detecting lane lines. First, we need to consolidate the scramble bunch into two separate lanes, and to do that, we need to know which lines belong to the left lane and which lines belong to the right. The huelines function returns an array of rho and theta values, so if we can parse the data and filter out lines of a certain angle, we can effectively separate our two lanes. Let's make a new function here called parse, which will do just that. We'll feed it the lines array, a target theta value, and a percent deviation which will act as a threshold. While we're at it, let's use this array to find the average rho and theta value for a given set of lines. Printing the contents of the lines array shows us that our two line groups occur at theta equals 0.7 and theta equals 2. We'll set the percent deviation to 40. Now all we gotta do is adjust our code, plot the two lines, and presto. Looks much better. I color-coded the left lane orange and the right lane blue. Now our code works great with the still image, but what if we try a video? Let's change the target file to open up the first video. Running our script gives us some sketchy results, with our lane swinging to the side of the screen. What's going on is that as the vehicle moves, the dotted left lane becomes harder to track. In order to fix this, we need our code to be able to remember where the lane was. That way if it can't find the lane, it can at least take a guess as to where the lane might be. Let's initialize arrays to store the last known location of the lane line. Now in our loop we'll set a condition. If the left lane has an angle equal to 0, we'll send through the last valid lane parameters. We'll do something similar to the right lane to prevent it from jittering as much. Let's run the script. Now our lanes aren't doing the hokey pokey. Awesome. Okay, one last video. Giving it a try with our last script, our left lane is way off, and our right lane doesn't show up at all. We can try adjusting the sensitivities on our huelines and parse functions, but still no luck. So what's happening here? If we take a look at our edge frame, we should see the lines that Python sees, but right now it's just a big white trapezoid. This tells us that our video is too bright, as it sees the entire snip as one big line. So let's dim the video. We'll create one more function called dim image, and it'll do just that. We'll adjust the gamma value of each pixel using the cv2.lookupTable function. Now let's run our code again. It's not perfect. The left lane's still a bit jittery, and the right lane could have some trouble finding the line, but it's much better from what we saw earlier. And that's the lane detection script. It's still pretty fundamental compared to what you see on board semi-autonomous vehicles, as those can detect curves in the road, oncoming signs, and other vehicles. The Raspberry Pi itself is also pretty limited in terms of power. Doing these kinds of functions on the Pi in real time can be quite taxing, so we'll stick to processing these pre-recorded videos for now. Although Python isn't the ideal language for an autonomous car, due to its slow compiler and large memory usage, it's still good exercise in learning the capabilities of OpenCV.